Okay, hello. Let's continue with biophysical models for FMI, and I think we might actually finish this description of the deterministic aspects of dynamic causal models for FMI today, and then from next time on we'll be able to talk about inference on these models. So what is still left for discussion are the hemodynamic state dynamics. Why not just call them the hemodynamics of these models? And as you remember, these models apply to different regions, or they use data from different regions and then model the behavior of these regions, the biophysical behavior of these regions. And for each region there are 5 state variables, as we've now seen repeatedly, where the first state variable of each region models the neural activity in this region and is coupled to the neural activity in the other regions, while the remaining 4 state variables, so x2, x3, x4, and x5, model the hemodynamic states of the ith region, so of a single region, and there's no coupling of hemodynamic states assumed in this model between regions. So to make this a little bit simpler in terms of notation, I will drop the superscript and discuss everything for one region, which is then not indexed by I, but keep in mind that these state variables, the hemodynamic state variables, exist for all I from 1 to the number of regions. And also to simplify things, I'm defining a new state vector here, which comprises the 2nd to 5th state variables. So these are all hemodynamic states. And then at the end of the last session, we already introduced the functional form of the evolution of these hemodynamic states, and they can be captured in a evolution function, and I'm just writing it up again and then we discuss it. So the evolution function, again, like always in dynamical systems, specifies the rate of change of the state vector at a given time point, and here this rate of change is also, like always, a function of the state vector at the time point t, so at a given time point itself, and this is here 4-dimensional because there are 4 hemodynamic state variables. Then it's a function of the neural activity in that region, so the x1, and it's a function of some parameters which belong to this overarching evolution function f that we've discussed previously. And then what it returns is the 4-dimensional vector of rate of change, like always in dynamical systems, evolution functions, and spelling that out, our x, which now contains x2, x3, x4, x5, x1, which is the neural state of the ith region, so don't get confused, it's only, of course, only of the ith region, that feeds into the hemodynamics of the ith region, and some parameters theta f, which I denote by 2 because these are not the ones that affect the neural evolution, but the hemodynamic evolution can also have, well, I don't want to use an h because my h is this overall function. Anyway, so it's just some additional index. And so these get mapped onto the rate of change, and this then is specified as follows. And how do we do it? Maybe we do it step by step. So we first now look at the first two and discuss what this is about. So I'm just writing them up in here. And once we've done that, we write them up again. So the first two the first two hemodynamic states evolve according to this specification. I don't write the other ones right now because let's focus on them for the moment. And as I already mentioned last time, they model a vasodilatory signal and blood flow. And so maybe let's look at this in a little bit more detail before we go to the other ones. So what this says is that our second state variable in each region is described by its rate of change, and this rate of change depends on the first state variable, which is a neural activity, some parameter kappa s, and itself, and some other parameter kappa f, and x3, and x3. The rate of change of x3 is given by x2 divided by x3, and this is again vasodilatation and blood flow. So what can we say from looking at this? And this is essentially what we will do today, trying to get a little bit of an understanding of what these equations are about, always keeping in mind that the equations could be different if we wanted to make them different. That in a way we also didn't invent them, so some people thought that this would be a good idea. So this goes back to the work of, for example, Buxton in 1998. One can do things differently if one wants to, but trying to get some kind of understanding of what's going on. So what we see for the rate of change of vasodilatation is that it's positively modulated by neural activity. So that's neural activity here, meaning that if neural activity goes up, or has a high value, then the vasodilatory signal, or this vasodilatation state, changes positively. It's fairly straightforward. So it means neural activity goes up. There is an increase in the vasodilatation. Then there is some self-inhibitory dynamic. So if vasodilatation goes up, it's also increasingly inhibiting itself. So it will not grow infinitely. So one way to think about this is that the rate of change, so that there's some kind of depletion process, that there's vasodilatory signal released, and then the more that is released, the less still can be released, and at one point it's empty. However, you should also be aware that this is, of course, the model is silent on how that works on the molecular level or the cellular level, right? So it's just describing some numbers which are coupled, and what this then really means in terms of the biology, one would have to justify based on the biological literature, for example. But that's that's what one can do in addition. And And then there is even more inhibition accounted here for by the blood flow. This little tilde that I put on it, this is this exponentiation, which always turns the blood flow into a positive, makes it a positive constant, a positive number. The whole thing means that the stronger the blood flow gets, the larger the blood flow gets, the vasodilatory signal changes negatively. With these are always then time constants. So there is some feedback in terms of the blood flow to the vasodilatation. How this is now again thought out from a cellular, biomechanical, or molecular biological perspective is not further specified. Yeah? So I don't know. It could be that if there's a lot of blood flow into a region, that this biomechanically excites certain receptors that then stop the further dilatation. It's silent on that. Maybe if you read the original papers, you find more on that. I tried a couple of times, but I've never really spent that much time on the whole thing of the hemodynamics as one might should. But if you just try to quickly get from these papers what the idea is, it's also not that easy, because it's not necessarily quickly clear. So that would require a little bit more work to get at an intuition what this would mean on a biomechanical, or molecular cellular level. The important, or the biggest thing that I take from this here, from the vasodilatation, is that if neural activity goes up, vasodilatation is induced, and vasodilatation is not induced at infinity, so that it's always just getting more and more dilated, and at one point the blood vessel is as big as the world, but it's inhibited by itself and also by the blood flow. So essentially this the main thing of this vasodilatory signal here is that it links neural activity on the one hand, and then namely in this thing here, blood flow on the other hand. So here the vasodilatation feeds into the rate of change of the blood flow variable. And if it's positive, then the rate of change of the blood flow is positive, so it goes up. And in this case, the blood flow inhibits itself not by means of subtraction, but by means of a division. So if the blood flow goes up, its rate of change is diminished strongly. I don't have a good story about why it's here by means of a division and not by means of a subtraction. There might be mathematical reasons, whatever that means, but I just don't have a story. Sorry. It's a nonlinear kind of inhibition, so it's pretty strong. If the waves are large, whatever. I don't have a good story about that. What this whole thing means in terms of the dynamics, depending on the parameters. This is also one thing, of course, this all depends on how you then set the free parameters, like these kappa parameters. About these two things, we can have a look, because one can integrate this. I should go to the figures, but it doesn't really matter. Oops. So what I plot here are all the hemodynamics, and we will get to all of them. Currently, we have had a look at the neural activity. So the neural activity I here describe just by this bump here at time 0. So it's a Gaussian bump again, if you want. So this is neural activity. And in blue, yeah, thanks. Oops, maybe I should have closed that. In blue, I plot the vasodilatory signal in the blood flow, and what you can see here is that the vasodilatory signal quickly grows, and then also gets below baseline at one point, and then returns to baseline. The blood flow here getting high. It gets negative here, but so it enters, so that's maybe to make that transparent, it enters these evolution equations always as a positive constant, but itself can of course get negative, as you see here. So it's just exponential if it's entering the evolution function. Yeah, so essentially, really what this means is neural activity goes up, vasodilatory signal goes up, and blood flow goes up, and then down again. So the interesting thing here is maybe by choosing some time constants to make this kind of like it's actually behaving in real experiments. But in addition to that, I don't think there's much kind of functional interesting aspects to this. It just goes up and then it goes down again. Like life in general. And then it goes up again. But then it goes down again. And so on. And in the end it goes down. Good, so this is kind of this vasodilatation blood flow aspect, which is modeled for each region. And then there is the additional aspect that now links blood flow to venous blood volume and deoxyhemoglobin, because from just vasodilatory signal and blood flow, when you think about the MRI system and that the T2 star is sensitive to deoxyhemoglobin content, of course you cannot really predict MR bold signals yet, so it needs a little bit more, and the little bit more is following now. So the fourth state variable, which models blood volume, is evolving according to this equation. And so that's blood volume. And then we have deoxyhemoglobin content, which is evolving according to this equation. Which then completes the specification of this function, of the evolution function of the hemodynamic states. So let's spend a little bit of time looking at these equations. So first, the rate of change of the venous blood volume. And here the idea is that there is some inflow. So that was blood flow, and this is here interpreted, of course, as the blood inflow. So how much blood flows into the venous compartment, and here this is the blood volume as it decreases, so that's interpreted as the blood outflow. And as far as I understand it, the main aspect here is this exponent, which basically scales the blood outflow in a nonlinear way. So that means that it's not, so if you have for example, if you plot x4 here and you plot x4 to the power of 1 over alpha here, it's not the identity mapping, but it's nonlinear, and then of course it depends on alpha, and the easiest thing or the basic thing is of course to think of something like x square. So if alpha is 0.5, then this is x square. So the larger the blood volume gets, the more it expels it, and this is what they mean by, or this is what they call balloon property. So the blood is expelled at a greater rate when this balloon is extended than if it's not extended. Then the interpretation of this parameter alpha is the stiffness of the whole thing. So if it's high, then the whole thing is very stiff, and this balloon effect doesn't really play a role. If it's very low, then it's fairly flexible, and this balloon effect plays a larger role. So blood inflow, blood outflow, in terms of the venous blood volume decreasing. Again, it's inhibited also by itself here in terms of this factor, and tau 0 also has a meaning. It's the time constant for this entire process, so that's why they interpret it as the mean transit time of blood through the venous compartment. At this point I mainly rely on what people wrote about it. I haven't really studied these equations in any further depth. The important thing again here is that it's linking blood flow to venous blood volume, and trying to capture some balloon properties which some people may think exist in the data, so that this is kind of justified as a modeling assumption. And then finally the last state variable being the deoxyhemoglobin content, described by this fancy equation. So tilde still means exponentiation, so that it always enters these things positively. Oops, there's something missing. So here now the deoxyhemoglobin concentration is affected by the blood flow. So the rate of change of the deoxyhemoglobin is affected by the blood flow in some way that looked fairly interesting. I haven't really studied in any analytical sense. So if, I mean, we will have a session on that. Maybe you are up to providing further insight into that once we talk about this in the programming aspect. One would have to actually sit down and look at, plot these functions. And get a good, if one wants, get a better intuition of what this means. The point is, at one point, one is then left with functions, and one doesn't really know anymore how this relates to the biology. The thing is, blood flow affects the hemoglobin concentration, and then the main thing is that and let's try to get it clear. So if the blood volume increases, then deoxyhemoglobin decreases, which of course captures this idea, and now I hope I don't say anything wrong, that deoxyhemoglobin is decreasing when you have neural activity. No? You are happy? Good, so no protests right now. So what this whole thing, let's keep it at this, what this whole thing tries to describe is that deoxyhemoglobin is decreasing as a function of increases in blood flow and blood volume, and to get to something like that behavior, you need an equation like that. Sorry, I don't really have a better explanation for this. But I can visualize that, and then it gets somewhat intuitive. So in red, we have the blood volume and the deoxyhemoglobin, blood volume as a dashed line and deoxyhemoglobin as a full line. And you see that blood volume is increasing with some delay after the blood flow, which also makes sense, but of course which also requires the right constant. And the deoxyhemoglobin, given its nonlinear evolution function that we just saw and only superficially understood, there's a decrease in deoxyhemoglobin. And in the end, this is what we want if we want to model what we know about the hemodynamics and their coupling to the MR signal. So in a way, so the way I'm looking at it right now is that the main motivation for these equation, or essentially for all the hemodynamic evolutions, is that they recreate what we have learned in our introduction to fMRI about the Bolt signal and its relation to vasodilatation, blood flow, blood volume, and deoxyhemoglobin content. And that from my perspective right now, maybe also because I don't have further insight, but maybe if I looked more, it wouldn't change that much. They mainly try to capture that vasodilatation in the end leads to a decrease in the deoxyhemoglobin content, and somehow you need to cast that into equations. And then you can, of course, try different kinds of equations, and some will work and some will not work. And then in the end, you have some equations that capture that, and then you are happy. The question is how much you understand then how much one can understand the equations. Although these are not too hard or complicated, but yeah, getting to this and see how it changes depending on x3, e0, and alpha, x5, and x4, and so on. Also not completely trivial, at least from my perspective. Okay, yeah, but that's the main thing about the hemodynamics. So here for these, for the hemodynamics here, I specified parameters. So the vasodilatory signal decay rate to be 0.64, the blood flow based, whatever, blood flow based feedback on vasodilatation as 0.41, mean transit time for the blood through the venous compartment of 2, vessel stiffness alpha 0.32, so you see that it's a more than square relationship. The oxygen extraction at rest, which is this E0, like that. And these were all the parameters. And of course, you can either infer these parameters based on data, or you fix them so that actually this kind of behavior happens. I wouldn't put my hand into the fire for that, but I think that these parameters actually have tight priors in the SPM implementation, although I would not completely. So the question is always, does DCM for fMRI, as it's done in SPM, estimate the hemodynamic parameters for each region so that you have different hemodynamic parameters, or does it use fixed parameters, or does it fit the different parameters over regions, so take an average over regions, and this is never really anywhere really documented, and one really would need to look into the code. And for DCM for fMRI, I haven't delved into the SPM code that deep. I did it for EEG, but then I decided I have now delved enough into the SPM code. So in a way, this is what should be documented in papers that really want to do DCM for fMRI. They should be clear about what's going on with these parameters, because all options exist, right? So you can, in principle, you can try to estimate all hemodynamic parameters for all regions, or not. Yeah? However, if you leave them to, the other thing is, if you leave everything up to be estimated from the data, you might end up with parameter regimes that don't, because here obviously this is based on fixed parameters, that don't reproduce these dynamics anymore, so that you don't actually have a deoxyhemoglobin content decrease after neural activity, and then maybe that's not actually what you want. So maybe you actually want to fix the parameters. But these are then interesting model considerations that are important when you actually use these models for data analysis. Good. Questions about the hemodynamics? But not why E0 is like this and then there's a 1 minus. I don't have any more to say about the details of these equations. General questions I'm very happy to answer.
Those are very general questions about the figure. Or maybe it's easier to answer with the figure, because we have those 5 different states. The question is, which of those are observed? Are they all observed?
No, actually none of them are observed. So these are all the latent states. So this is our f, x, u, theta, f. So none of the x states are observed. We haven't talked about that yet, but they are all latent. They are not observed. Of course, you can do experiments where you measure, for example, blood flow, for example, also using MRI, or you measure, if you're doing this in vitro or in some animal preparation, you measure vasodilatation. You could potentially observe them, but in DCM for fMRI they are of course not observed, because the only thing that is observed is the MR signal. It's not even the deoxyhemoglobin content, it's the MR signal, which we still have to specify how it arises from this. Yeah, but it's a good question. All latent states, all theory or explanation of observed data. Other questions? No. Good. So in the very beginning, or not the very beginning, but at one point, we discussed the overall shape of DCM5MI, and we just got back to it. So we said that F models the evolution of latent states, and these were our neural dynamics that we discussed last time, and our hemodynamics for all regions. And we so far we have only discussed this. And remember that there are as many latent states as there are regions times 5, because each region has 5 state variables. So, for example, this describes a 15-dimensional dynamical system if there are 3 regions. And then finally, so this is all at the latent level, but in addition, we discussed that there is a mapping that takes the latent states, takes some parameters, and maps those onto Z, which serves as the high temporal resolution prediction of the MR signal. And this is what is called the observation function. And in principle, then, this is observable although, of course, what's actually happening is that the whole thing is then still downsampled and embedded in a probabilistic model. So what is actually observed are realizations of random variables of these of the likelihood function of DCM. But of course, this is much closer to observable than the latent states, and we don't talk about the probabilistic embedding much yet. So the important thing is now how these latent states are mapped to something that is in principle observable. And these kind of observation functions, they can be more or less complex. So, for example, in DCM for EEG, these observation functions relate to how the electrical activity of a certain region in the brain is propagated to the electrode level, so they can be quite complex. In DCM for FMI, which we are dealing with here, they actually are somewhat straightforward, if, however, not that nice to understand, at least from my perspective. So there is this observation function, and this observation function is regional specific. So we've seen that also at a previous time point, but maybe I'll write it up again. So the observation function takes the whole number of state-dimensional state vector. So, for example, a 15-dimensional state vector, if there are 3 regions and each of them has 5 states, like always, and a parameter vector, and then it maps the state vector onto a number of region dimensional vector, and this is what we will look at in a second. So there are a number of regions observation functions. And each of these observation functions, gi, where I goes from 1 to the number of regions, takes the entire state vector and parameters. So this is now something different. So this is the overall observation function. This is the regional specific observation function, and maps this onto a real number. And that's the first and very important thing about the whole thing. So the observation function takes the 15-dimensional system, for example, if you have 3 regions, and maps it onto a 3-dimensional system. Yeah. So it does. So you have this very big latent state vector that is at least 5-dimensional if you have only one region, and this 5-dimensional state vector is mapped by the observation function if you have only one region onto a single number. And if you have more regions, then you have, of course, always 5 times more latent variables, but the observable level has as many observable values per time point as their regions. Yeah? So it's a kind of, it reduces this high dimensionality of the latent level to the actually observable level or number, the dimensions of the observable level, which needs to be done. Yeah.
Okay, so on theta G, sorry, because the G wasn't there before, so that makes sense.
Sorry. And how does it look like? So the thing is of, so this ith observation function, in a way it only looks at the, at the hemodynamic states in the ith region. So one could also pass to it only the ith part of the state vector, but this, I mean, if you do that, it depends on in the end how you actually implement it. It would require, I mean, we could also write here x1, x2, whether you give it the whole thing or just a subpart. If it then in its evaluation only looks at the subpart anyway, it doesn't really matter. The most interesting thing is, of course, still its functional form, and this looks as follows. It takes the deoxygenated hemoglobin signal. That was the last hemodynamic state, so the 5th hemodynamic state of the ith region. It takes, so these C's are constants. It takes the ratio of the deoxyhemoglobin in the ith region with the blood volume in the ith region, and it takes the blood volume. And in addition, so basically, so this let's just notate that here. That's the oxyhemoglobin. This is the oxyhemoglobin times divided by volume, and this is the volume. And then it requires these constants, which are actually, yeah, they must be constant over the regions, I think. Although, and this is really annoying that I can't really tell you that, because this should be in all the papers, but you don't find it in the papers, so you would have to find it from the code. So it takes something about the imaging process, so the TE, C2 also takes information from the imaging process, and C3 is just like this, because we have done there 1 minus epsilon 0, which is some, back to that, as you see, I didn't invent this, so I also wonder what all of this is. E0 is the, no, that's not the E0 that I mean. E0 is the resting state, oxygen extraction, rest, oxygen extraction. But I'm looking for this epsilon 0. So yeah, epsilon 0 is the extravascular bolt contribution. So this now takes into consideration how the observed MR signal is actually created inside the sample of interest. So there are contributions to both which come from intravascular and others that come from extravascular. And it takes this into account. R0 is the intravascular MR signal relaxation. TE is the echo time. mu0 is the MR frequency offset, whatever that is. And there's one other thing, no, only it's a 0 we have. I'm missing something else here, TE, E0. So, what's the main point of this? Nu0 is the frequency offset at the outer surface of magnetized vessels in Hertz. So what I take from this, also again, because I didn't go further beyond into this, besides noting what these things should be and how the function looks like so that I can implement that. What I take from this is that this is a model that takes into account both biological aspects. So you have here what's happening in terms of the hemodynamics, and it takes into account physical aspects of the imaging process, so the TE, some idea of how the bolt signal is created in a vascular coupling. So it does this kind of biological physical imaging process coupling. Yeah. That's what I take from it. The question about its specific form, I think this also goes back to the Buxton papers from the late 90s. There is a paper by, if you are really into this, there's a paper by Buxton, late 90s, but there's also a paper from Klaus Enno Stephan from 2007 that uses the whole DCM framework to look at different forms of these observation functions, because this is by no means the only observation function that you can try to use to link deoxygenated hemoglobin to the MR signal, because perhaps you can come up with other things. And then you actually are more in what I would call research than actually teaching. Because, yeah, going deeper into this would mean also for myself that I would start to write on the biophysical coupling of deoxygenated hemoglobin to the MR signal. And if I want to do that properly, of course, one needs to go deep into that, and then one does research. So I stop at this level here. If anyone wants to do a master thesis on this, you're very welcome. I mean, you had this master fair last week, right? So for everything in terms of master thesis, if you really feel like you want to do a master thesis on anything that I teach or work on, talk to me. My impression is it's not really, you all have other things in mind that is more clinically relevant, for example. Anyway, briefly skipping over this aspect, going back to our graph. So the main point that I take from this observation function is that it takes these two hemodynamic state variables and creates this Z thing here. And of course, this Z thing looks fairly familiar. It peaks after 4 seconds. It has a post-neural activity undershoot, so a post-stimulus undershoot, if you call the neural activity here the stimulus, and then returns to baseline roughly at 16 seconds. So it's actually the familiar model for the hemodynamic response function that we've already seen, but created in a completely different way, because we saw it in terms of the GLM being created by 2 gamma functions, gamma probability density functions, which don't have anything to do with that, but result in a similar shape. So the whole point, if you are annoyed already now by DCM5MRI, the whole point of X2 to 5 and the observation function is to link the neural activity to this in a mechanistic biophysics, meaning the MR signal generation process manner. And of course, what this allows you to do is to have a theory of how this process happens, and then, in principle, use empirical measurements to inform this process. Yeah? And from my perspective, it's a nice aspect for science. Might not be the aspect that you are most interested in, but it shows or it showcases how you can use available knowledge, come up with a theory, and then have a theory, and then of course in a way can also challenge this theory and say, okay, why this equation like that and not different? Why can we have another exponent here, and so on? And then you're really talking about science. Yeah, so you're talking really about the details of how things might mechanistically happen, and that's then interesting from my perspective. Yeah. I think I want to leave that at that, because I also don't have much more to say about this actually. Maybe at one point I spend much more time on this and go more into the details. So, it's of course a process, so it's about neurovascular coupling, right? The hemodynamics, so going from neural activity to the Bolt signal is neurovascular coupling. And if you are a neuroscientist, you might be more interested in is actually what's happening in terms of the neural interaction rather than this aspect. But of course, if you're measuring Bolt signal, you might as well have to look into that. Good. Any questions about this neurovascular coupling business right now?
So maybe coming back to the question. So in principle, this is observable. So the Z is in principle observable. However, we are doing this whole thing in high temporal resolution, so it needs to be downsampled, and it needs to become the expectation of a random variable. And what is then observed is a value of this random variable. No? Good. So then let's have a break, as we also overrun, but this is kind of, it's like Game of Thrones. The last episodes get a little bit longer. Not necessarily better. But that's a different topic. So let's have a break now until 9:10, and then I will show you an example of the whole thing and also show you how this is implemented so that you get a little bit more of a feeling of what's actually going on.